48 hours separate humanity from an answer that could redefine existence itself. On the 29th of October 2025, an object from beyond our solar system will pass through a cosmic crucible that may finally reveal its true nature. Not through speculation, not through hope or fear, but through physics, through measurement, through the cold mathematics of energy and motion that govern everything in the universe. Dr. Michio Kaku, theoretical physicist, has drawn a line in the cosmic sand. In his October 2025 statement, Dr. Kaku explained, "If it picks up extra energy as it whips around the sun, that would be outside the ordinary bounds of conservation of energy. That would mean, in no uncertain terms, that some intelligence is guiding it. This is not idle conjecture. This is a testable hypothesis. If the object designated 3I Atlas gains more kinetic energy during its solar passage than gravity alone can provide, if it accelerates beyond what the equations predict, then the natural explanations fail. And when natural explanations fail, what remains? The moment of truth arrives tomorrow, the 29th of October 2025. Perihelion, the closest approach to our star, at a distance of 1.36 astronomical units, roughly 204 million kilometers from the solar surface. At this distance, the object will be bathed in radiation intense enough to trigger profound changes. Live Science reported on October 26 that 3I Atlas is about to become very active. The solar heat will drive volatile materials from its nucleus into space, creating opportunities for observation unlike any that have come before. Telescopes across 7 continents are aimed at a single point in the sky, waiting for the cosmic visitor to reveal itself under the sun's unforgiving glare. But activity is only part of the story. The chemistry is what keeps scientists awake at night, what makes them question assumptions they thought were settled. On the 27th of October 2025, Space.com published findings that challenge our understanding of what interstellar objects should look like. Thank you for being with us. Please subscribe and leave a like. A team led by Dr. Daryl Seligman, physicist, detected something that defies easy explanation. Using the Very Large Telescope in Chile, they found glowing nickel vapor surrounding 3I Atlas at a distance of 3.88 astronomical units from the Sunday. Dr. Seligman stated in October 2025, "In a surprising discovery, our team has detected glowing nickel vapor in the gas surrounding the incoming interstellar comet 3I Atlas at an extraordinary distance from the Sun, where temperatures remain far too cold for metals to normally vaporize." Read that again. Too cold for metals to vaporize. At 3.88 astronomical units, the ambient temperature should keep metals locked in solid form. The process of sublimation, where solid transforms directly to gas, requires specific temperature thresholds. Nickel should not be glowing in space at that distance. Yet there it was, streaming away from the nucleus, defying the rules. The scientific team proposed that nickel might be bound in specialized molecules, compounds where metal atoms attach to carbon monoxide or organic molecules that break apart easily under sunlight. This would allow metal release at lower temperatures than direct sublimation requires. It is a natural explanation for an unnatural observation. But there is more to this chemical mystery. The compound being detected is nickel tetracarbonyl, a molecule consisting of one nickel atom bonded to 4 carbon monoxide molecules. This substance has a very specific history in human knowledge. It is used in the Mond process for purifying nickel metal, a technique developed in the 19th century for industrial manufacturing. Nickel tetracarbonyl is toxic, volatile, and familiar to chemists who work with metallurgy and materials science. It exists in refineries and laboratories where metals are purified and processed. What it is not is natural. It has never been detected in a comet from our solar system. It has never been observed in asteroids or in the diffuse clouds between stars. Only in human industry. Until now. Until 3I Atlas. The implications ripple outward, like waves from a stone thrown into still water. If this compound forms naturally in interstellar space, if conditions exist somewhere in the galaxy that produce nickel tetracarbonyl through processes we have not yet identified, then our understanding of cosmic chemistry requires expansion. If it does not form naturally, if its presence in 3I Atlas represents something else, then the questions become more profound and more troubling. Dr. Avi Loeb, astrophysicist at Harvard, has been monitoring this object with an intensity that borders on obsession. In late October 2025, he issued a warning that resonated across the scientific community and beyond. He called 3I Atlas a potential black swan event. The term comes from risk analysis and refers to occurrences so rare and impactful that they fall outside normal expectations, yet seem obvious in retrospect. The discovery of fire was a black swan, the invention of agriculture, the splitting of the atom, events that reshape civilization's trajectory, events that divide history into before and after. Dr. Loeb went further. He compared 3I Atlas to a Trojan horse, invoking the ancient Greek tale of a gift that concealed an army within. Something that appears one way on the surface, but contains hidden purpose beneath. In the tale, the Greeks besieged Troy for years without success. They built a wooden horse, left it at the gates, and sailed away. The Trojans brought the horse inside their walls as a trophy. That night, soldiers hidden within emerged and opened the gates for the Greek army waiting in darkness. The analogy is deliberate and provocative. It suggests that 3I Atlas may appear natural, may display features consistent with cometary behavior, yet contain within itself systems or purposes that are anything but natural. It raises the possibility of deception, intentional or emergent, where the object's true nature is concealed beneath layers of ice and dust and outgassing that mimic what we expect to see. According to Dr. Loeb in October 2025, it's at least 1,000 times more massive than the previous interstellar objects we've seen. And the question is, why has such a giant object entered our solar system now? 33 billion tons. The mass calculated from data provided by the James Webb Space Telescope. To put this in perspective, the first interstellar visitor, Oumuamua, discovered in 2017, was perhaps a few hundred meters across and likely weighed millions of tons. The second, 2I Borisov in 2019, was similar in scale, a relatively small chunk of material ejected from another star system and wandering the galaxy until chance brought it through our cosmic neighborhood. But 3I Atlas is approximately the size of Manhattan, 1,000 times more massive than anything from beyond our solar system that humanity has ever observed. The scale alone demands attention. Objects of this size do not form easily. They require specific conditions, gravitational environments, where material can accumulate and compact over millions of years. They require protection from disruptive forces that would shatter smaller bodies. Why this size? Why this mass? Why now? These questions lack satisfying answers. Dr. Loeb frames them not as rhetorical, but as genuine scientific puzzles requiring investigation. If 3I Atlas represents the typical scale of interstellar objects, then Oumuamua and 2I Borisov were the anomalies unusually small fragments rather than representative samples. If 3I Atlas is the anomaly, unusually large compared to the background population of interstellar travelers, then its arrival demands explanation beyond simple statistics. The trajectory adds another dimension to the mystery. Most objects entering from interstellar space should arrive from random directions, their paths determined by the chaotic history of their ejection from origin systems and their subsequent journey through the galaxy. The vast majority should have no particular relationship to the geometry of our solar system, to the flat disk of the ecliptic where planets orbit. But 3I Atlas does not follow this expectation. Its trajectory lies roughly within the ecliptic plane, approaching the Sun in a path that suggests familiarity with our system's architecture. This could be coincidence. In a large enough sample, improbable events occur regularly. Roll dice enough times and eventually you will see long sequences of the same number. Observe enough interstellar objects, and eventually one will arrive aligned with the ecliptic. But the probability matters. If ecliptic-aligned arrivals occur in 1% of interstellar visitors, then 3I Atlas represents chance. If they occur in 1/10 of 1%, the coincidence becomes more notable. If they occur even less frequently, then alignment suggests either extraordinary luck or deliberate targeting. The global response has been unprecedented. The International Asteroid Warning Network, coordinated with NASA and space agencies around the world, launched a major observational campaign announced on the 21st of October 2025. The campaign runs from the 27th of November 2025 through the 27th of January 2026, representing the first time in history that the international community has organized a structured, coordinated observation effort for an interstellar visitor. Professional astronomers and citizen scientists are invited to participate. Workshops scheduled for November 10 will train observers in high-precision astrometry, the measurement of position, speed, and motion against the background stars. The precision required is extraordinary. To predict where 3I Atlas will be months from now, to determine whether its trajectory follows purely gravitational paths or includes non-gravitational components, measurements must be accurate to fractions of an arcsecond. An arcsecond is 1/3600th of a degree. Achieving this precision with ground-based telescopes requires accounting for atmospheric distortion, for instrument calibration drift, for the motion of Earth itself as the planet rotates and orbits. It requires software that can identify the same background stars in images taken weeks apart, that can measure pixel positions and convert them to celestial coordinates with sub-pixel accuracy. Space.com reported on October 27 that this campaign serves a dual purpose. The observational campaign is being used as training ground for planetary defense, to track speed, motion, and predict orbits of potentially hazardous objects. Comets present unique challenges because their tails and comas affect brightness estimates and complicate trajectory calculations. The cloud of gas and dust surrounding a comet's nucleus creates a fuzzy appearance that makes pinpointing the exact center difficult. When an asteroid is photographed, it appears as a sharp point of light. Software can identify that point with high precision. When a comet is photographed, it appears as a diffuse glow, with brightness fading gradually from center to edge. Finding the exact position of the nucleus buried within that glow requires modeling the coma's shape and brightness distribution, subtracting that model from the image, and locating the residual bright spot that marks the solid body. 3I Atlas provides an opportunity to refine these techniques against a large, active target. The comet size means the coma will be substantial. The outgassing will be vigorous. The brightness variations will be complex. Learning to extract precise positions from observations of 3I Atlas improves our ability to track any comet that might pose an impact threat in the future. But there is a question beneath the question. If 3I Atlas poses no danger, why the urgency? NASA has stated clearly that the object presents no collision risk to Earth. The closest approach to our planet will occur on the 19th of December 2025, at a distance of 1.8 astronomical units, approximately 270 million kilometers away. At that distance, 3I Atlas poses no more threat than Jupiter does on its closest approaches, which is to say, no threat at all. There is no danger of impact. And yet the world's telescopes turn as one. Resources are allocated. Observation time normally dedicated to other projects is redirected toward this single target. The level of attention suggests that scientists recognize something extraordinary about 3I Atlas, something that transcends routine cometary observation. Dr. Loeb has offered a hypothesis that pushes beyond the boundaries of conventional astronomy. If 3I Atlas were not a comet but a mothership, it could use the sun's gravity to release smaller probes through a maneuver called the Oberth effect. This is real physics, not science fiction. The principle is well understood and has been used by human spacecraft for decades. The Oberth effect exploits the relationship between kinetic energy and velocity. When a spacecraft fires its engines while moving slowly, it gains velocity, but the energy efficiency is relatively low. When the same spacecraft fires its engines while moving very fast, it gains the same velocity change, but the kinetic energy increase is much larger. This is because kinetic energy depends on velocity squared. Doubling velocity quadruples energy. At perihelion, 3I Atlas will be moving at its maximum speed relative to the Sunday. If it were a spacecraft, if it possessed propulsion systems, firing those systems at perihelion would yield maximum energy return for minimum fuel expenditure. A small burst of thrust applied at the right moment could dramatically alter the trajectory, converting a hyperbolic escape path into a bound elliptical orbit. Or it could launch smaller craft towards specific targets within the solar system, giving them initial velocities that would require far more fuel to achieve from a standing start. Human missions to Jupiter, Saturn, Uranus, and Neptune all used gravity assists, flying close to inner planets to gain speed before continuing outward. Voyager spacecraft are now in interstellar space because careful planning of these assists built up velocity over years of flight. If 3I Atlas were artificial, if it carried probes designed to study the solar system, perihelion would be the optimal moment to deploy them. Tomorrow, October 29, the window opens. The tail adds another layer to the mystery. During July and August 2025, astronomers observed an anti-solar tail, a jet of particles and gas pointing toward the sun instead of away from it. This is rare but natural, an optical effect caused by specific geometries and dust particle sizes. Large dust particles ejected from a comet's nucleus follow slightly different orbits than the nucleus itself. When Earth's position allows us to view the comet edge-on to its orbital plane, these particles can appear to form a tail pointing sunward. A handful of solar system comets have displayed anti-tails over the history of telescopic observation. Comet Arend-Roland in 1957 showed a prominent anti-tail that made headlines and confused observers unfamiliar with the phenomenon. When 3I Atlas showed this feature in July and August, scientists noted it as interesting but explainable within known physics. Then, in September 2025, something changed. Images captured by the Nordic Optical Telescope in the Canary Islands documented that the anti-solar tail had reversed direction, becoming a regular tail pointing away from the sunday. The object's orientation had shifted. The geometry had changed. The viewing angle no longer produced the optical effect that creates anti-tails. Or something else had changed. Adam Hibbard, colleague of Dr. Loeb, offered an interpretation that crossed from natural explanation into speculative territory. According to Hibbard in October 2025, if the object is an alien spacecraft slowing down and the anti-tail is braking thrust, then this change from anti-tail to tail would be entirely expected near perihelion. In that case, the transition would constitute a technosignature in the form of an unexpected phenomenon indicative of controlled maneuvering. A technosignature, a sign of technology. The hypothesis suggests that if 3I Atlas were decelerating using some form of propulsion, the exhaust would create what appears to be an anti-tail. Then, after achieving the desired velocity reduction, the craft might switch to different thrust modes or shut down engines entirely, allowing natural solar wind and radiation pressure to create the observed directional change. This is speculation built on observation. The tail reversal happened. Multiple observatories documented it. The images exist in archives, time-stamped and calibrated. The interpretation of what it means divides the scientific community into camps that grow more polarized with each passing day. The division is not merely academic. It reflects fundamental disagreements about how science should approach extraordinary claims. The conservative position holds that natural explanations must be exhausted before considering artificial ones. The progressive position argues that artificial explanations should be evaluated alongside natural ones when observation suggests them, rather than being automatically relegated to a category requiring higher standards of proof. Dr. Loeb represents the progressive camp. His argument, repeated in interviews and papers throughout October 2025, is that the search for extraterrestrial intelligence should not be confined to radio signals. If technological civilizations exist, if they have developed space travel, then artifacts should be detectable, and the search for those artifacts requires willingness to consider that unfamiliar objects might have unfamiliar origins. The conservative camp counters that extraordinary claims require extraordinary evidence, and the evidence for artificial origin of 3I Atlas remains circumstantial. Each anomaly has potential natural explanations. The nickel emission could result from exotic molecular chemistry. The anti-tail reversal could reflect geometric and rotational changes. The large mass simply means this interstellar visitor happens to be bigger than previous ones. Taken individually, each anomaly can be explained naturally. The question is whether explaining each separately represents the correct approach, or whether the pattern of anomalies, the clustering of unusual features in a single object, suggests examining alternative hypotheses more seriously. This debate has precedent. It echoes arguments that occurred during and after the Oumuamua observations in 2017 and 2018. That first interstellar visitor exhibited anomalies of its own, most notably non-gravitational acceleration that could not be easily attributed to outgassing because no coma or tail was observed. Dr. Loeb proposed that Oumuamua might be a light sail, a thin artificial structure pushed by radiation pressure. The astronomical community largely rejected this interpretation, favoring explanations involving outgassing of hydrogen or other volatiles too faint to detect. The debate over Oumuamua never reached resolution because the object departed the inner solar system before sufficient data could be gathered. It is now beyond the reach of even our most powerful telescopes, a mystery receding into cosmic distance at over 26 kilometers per second. Whatever Oumuamua was, whatever secrets it carried, They are gone now, accessible only through the limited data captured during its brief passage through observable range. 3I Atlas presents an opportunity to avoid repeating that outcome. The object is larger, brighter, more active. Its trajectory keeps it within range of observation for months rather than weeks. The international campaign ensures coordinated coverage rather than scattered opportunistic observations. If 3I Atlas harbors secrets, humanity has the tools and the time to discover them. But tools and time are worthless without the will to use them properly. And that will is fractured by disagreement over what properly means in this context. The scientific community's reaction to 3I Atlas has been complex and multifaceted. In the immediate aftermath of the discovery in July 2025, excitement focused on the opportunity to study a third interstellar object. The first two had provided invaluable data about the diversity of material beyond our solar system. A third would allow comparisons, would begin to establish patterns, would help determine whether Oumuamua and 2I Borisov represented opposite extremes or typical examples of an interstellar population. As observations accumulated through July and August, as the unusual features began to reveal themselves, the excitement shifted toward puzzlement. The nickel detection at impossible distances prompted immediate theoretical work attempting to explain the phenomenon through natural chemistry. Papers appeared on preprint servers proposing molecular carriers, surface processes, exotic ices containing nickel compounds that might sublimate under specific conditions. These papers represented normal scientific response to unexpected observations. Build models, test predictions, refine or reject based on how well the models match continued observations. This process is ongoing. Dr. Seligman's team continues to gather spectroscopic data, continues to refine their models of how nickel vapor might form at such low temperatures. But a parallel response also emerged, quieter initially but growing louder through September and October. A response that questioned whether natural chemistry could fully account for what was being observed. This response came primarily from researchers involved in the search for extraterrestrial intelligence, from theorists willing to entertain possibilities that mainstream astronomy traditionally dismisses without detailed examination. Dr. Loeb became the most prominent voice in this camp, but he was not alone. By mid-October, a group of astronomers and physicists had formed an informal working group to evaluate the evidence for artificial origin. This group did not claim 3I Atlas was definitely artificial. They argued that the hypothesis deserved serious investigation rather than reflexive rejection. Their position rested on several pillars. First, the accumulation of anomalies. Each individual feature might have natural explanations, but the coincidence of multiple rare features in a single object reduced the probability that all explanations were correct. Second, the availability of tests. Dr. Kaku's energy conservation test at Perihelion provided a clear observable that could distinguish natural from artificial behavior. Third, the stakes. If 3I Atlas were artificial and humanity dismissed it as natural, the missed opportunity would be historically tragic. The mainstream astronomical community's response to this working group was mixed. Some researchers praised the effort as embodying open-minded scientific inquiry. Others criticized it as premature speculation that risked damaging astronomy's reputation by association with sensationalist claims about alien visitors. The criticism had historical roots. Astronomy has weathered numerous episodes where popular excitement about potential extraterrestrial phenomena created expectations that observations failed to fulfill. Each disappointment eroded public trust slightly. Each retraction of a dramatic claim reinforced skepticism about future claims. The pattern stretches back decades. In 1967, the discovery of pulsars, rapidly rotating neutron stars that emit beams of radio waves, initially sparked speculation about artificial beacons from advanced civilizations. The discoverers even nicknamed the first pulsar LGM-1 for Little Green Men. Within months, natural explanations prevailed, and the excitement faded. In 1977, the WOW signal, a strong narrowband radio signal detected by the Big Ear telescope, seemed to match expectations for an artificial transmission. The signal was never detected again despite extensive follow-up observations. Decades later, natural explanations involving comets or hydrogen clouds remain contentious but more accepted than artificial origin. In 1996, a team announced potential evidence of fossilized microbial life in a Martian meteorite found in Antarctica. The claim sparked intense debate. Most scientists eventually concluded that the features could be explained through non-biological processes. The meteorite remains controversial, the evidence suggestive but not conclusive. Each of these episodes followed a similar arc: initial discovery and excitement, claims of extraordinary implications, media coverage amplifying the drama, detailed analysis revealing natural explanations or undermining the evidence, quiet retreat from extraordinary claims, public disappointment, and increased skepticism. The lesson many astronomers drew from this history was caution. Extraordinary claims attract attention, but carry risk. If the claims prove unfounded, credibility suffers. Better to understate possibilities than overstate them. Better to emphasize the natural explanations and present artificial origin as a distant, unlikely alternative that cannot be completely ruled out, but should not be seriously entertained until all natural options are exhausted. This cautious approach has merits. It protects scientific credibility. It avoids creating false hope. It maintains standards of evidence that have served astronomy well for centuries. But it also has costs. Caution can shade into conservatism that dismisses legitimate anomalies too quickly. Fear of being wrong can prevent asking questions that might reveal profound truths. And in the specific case of searching for extraterrestrial intelligence, excessive caution guarantees we will never find evidence, even if it exists, because we will always find reasons to attribute ambiguous observations to natural causes. This tension between caution and openness defines the current debate over 3I Atlas. Both sides cite the same observations. Both sides claim to follow scientific principles. Yet they reach different conclusions about which hypotheses deserve serious consideration. The working group focused on potential artificial origin has outlined a research program for the coming months. The program includes several key observations that could provide evidence for or against technological origin. First, the Perihelion energy test proposed by Dr. Kaku. This requires precise measurements of velocity and trajectory before and after closest approach. If energy is conserved within measurement error, natural behavior is confirmed. If excess energy appears, further investigation is warranted. Second, detailed spectroscopic analysis of outgassing patterns. Natural comets release volatiles in patterns determined by solar heating of the nucleus. Artificial objects might show different patterns, perhaps more uniform across the surface, perhaps varying in ways that correlate with orientation rather than solar distance. Distinguishing these patterns requires extensive data gathered over weeks as the object rotates and moves. Third, searches for narrow-band radio emissions. Natural objects do not produce radio signals at specific frequencies. Artificial objects might, if they contain electronics or communication systems. The frequencies would need to be chosen carefully, Too low and interference from Earth-based sources overwhelms any potential signal. Too high and atmospheric absorption reduces sensitivity. The sweet spot lies roughly between 1 and 10 gigahertz. The range where Earth's atmosphere is relatively transparent and cosmic background noise is relatively low. Fourth, examination of surface features at maximum resolution. If 3I Atlas passes close enough to Earth, if atmospheric conditions permit, ground-based telescopes might resolve details on the nucleus surface. Hubble Space Telescope and James Webb Space Telescope could certainly resolve such details. Natural surfaces show irregular shapes, craters, ridges formed by gravitational collapse, and impact history. Artificial surfaces might show geometric patterns, straight edges, regular structures. Fifth, analysis of any material captured by spacecraft passing through the tail. If Europa Clipper or Hera collect particles, if those particles can be examined in detail either by onboard instruments or after return to Earth, their structure and composition could reveal whether they originated from natural ices or processed materials. Each of these observations is feasible. Each could provide data relevant to determining 3I Atlas's nature. The working group has proposed coordinating these observations, ensuring that multiple facilities target the object simultaneously to maximize data quality and quantity. The November through January observation campaign represents the implementation of this plan. The Minor Planet Center's announcement in late October formalized what had been informal discussions among researchers. By creating an official campaign with registration and workshops, the center legitimized the extraordinary level of attention 3I Atlas is receiving. The campaign timeline is driven by 3I Atlas's trajectory. Perihelion on October 29 marks the beginning of maximum activity. Through November, as the object moves away from the Sun but approaches Earth, observing conditions improve for ground-based telescopes. The closest Earth approach on December 19 provides the best opportunity for high-resolution imaging. Through January, as 3I Atlas continues outward and fades, long-term monitoring tracks any changes in activity level or trajectory. Professional observatories have committed substantial resources to this campaign. The Very Large Telescope in Chile will dedicate multiple nights to spectroscopic observations, building on Dr. Seligman's work to track nickel emissions and search for other unusual chemical signatures. The Gemini Observatory, with facilities in both northern and southern hemispheres, will monitor the object continuously to detect any sudden changes in brightness or structure. The Keck Observatory in Hawaii, with its adaptive optic systems that compensate for atmospheric distortion, will attempt to resolve surface features on the nucleus. Even at 3I Atlas's closest approach, the object will be small enough that resolving details requires pushing telescope capabilities to their limits. But if geometric structures exist, if the surface shows patterns inconsistent with natural formation, Keck has the best chance of detecting them. Radio telescopes are also involved. The Very Large Array in New Mexico will scan multiple frequencies, searching for any narrowband emissions. The Arecibo Observatory, before its collapse in 2020, would have been ideal for this work. The loss of Arecibo reduced humanity's radio astronomy capabilities significantly. The remaining facilities must work harder to achieve comparable sensitivity. The Green Bank Telescope in West Virginia, the world's largest fully steerable radio telescope, will also participate. Green Bank operates in a radio quiet zone, a region where terrestrial broadcasts are restricted to minimize interference. This makes it ideal for detecting faint signals that might be overwhelmed by noise elsewhere. Space-based observatories provide capabilities unavailable from the ground. Hubble Space Telescope will image 3I Atlas in visible and ultraviolet wavelengths, capturing details of the coma structure and searching for any unusual emissions. James Webb Space Telescope will observe in infrared, measuring the thermal signature of the nucleus and analyzing the composition of ices sublimating from the surface. Webb's infrared capabilities are particularly valuable for this work. Many molecules that are difficult to detect in visible light have strong signatures in infrared. If 3I Atlas contains organic compounds, if its chemical composition differs significantly from solar system objects, Webb can identify those differences. Citizen scientists form another crucial component of the observation campaign. Amateur astronomers with modest equipment can contribute valuable data if their observations are properly calibrated and coordinated. The workshops, scheduled for November 10, will train participants in standardized measurement techniques, ensuring that amateur observations meet professional quality standards. The distributed nature of the amateur network provides geographic coverage unavailable to any single facility. When weather closes an observatory, when equipment fails, when scheduling conflicts prevent observations, amateurs can fill the gaps. The accumulated data from hundreds of small telescopes can rival or exceed the data from a few large ones. This democratization of observation reflects a shift in how astronomy operates in the 21st century. Professional facilities remain essential for high-precision work, requiring specialized instruments. But much of the routine monitoring, the accumulation of light curves and positions over time, can be accomplished by amateurs with relatively simple equipment and sophisticated software. The 3I Atlas campaign may establish new standards for coordinated amateur-professional cooperation. If successful, it could serve as a model for future programs tracking objects of interest, whether those objects are potentially hazardous asteroids, transient phenomena, or other interstellar visitors. But success requires overcoming challenges. Coordination across time zones and languages requires careful planning. Data formats must be standardized, so observations from different sources can be combined. Quality control must filter out corrupted or poorly calibrated measurements without being so strict that useful data is rejected. The Minor Planet Center has experience managing such campaigns from decades of asteroid tracking work. Their infrastructure for collecting observations, assessing quality, and distributing results will be adapted to handle the unique requirements of 3I Atlas monitoring. The campaign also serves educational purposes. By inviting participation from citizen scientists, the campaign exposes a broader public to the methods and excitement of astronomical research. Participants learn about celestial mechanics, about measurement precision, about the careful work required to extract reliable information from noisy data. For many participants, 3I Atlas represents a once-in-a-lifetime opportunity to contribute to potentially historic observations. Even if the object proves to be a natural comet, even if no extraordinary features are discovered, the experience of participating in a coordinated international scientific effort has value. And if extraordinary features are found, participants will have been part of the discovery. The campaign also generates data that will be valuable regardless of 3I Atlas's nature. Detailed observations of an interstellar object's activity as it passes through the inner solar system provide insights into how such objects respond to solar heating. Spectroscopic measurements reveal chemical compositions that constrain models of formation conditions in other stellar systems. Trajectory measurements test our understanding of gravitational dynamics and non-gravitational forces. This data will be analyzed for years after 3I Atlas departs observable range. Papers will be published. Theories will be refined or discarded. Our understanding of the population of objects drifting through interstellar space will improve incrementally. But incrementalism is not what captures public imagination. The question on social media, in news articles, in conversations around the world, is not whether 3I Atlas will teach us about cometary physics. It is whether 3I Atlas will answer the oldest question humanity has asked: are we alone? The question of whether we are alone has haunted humanity since our ancestors first looked up at the night sky and wondered what lay beyond the horizon of visible stars. For most of history, the question remained purely philosophical. We had no means to search for answers, no technology capable of detecting life beyond Earth, no framework for thinking about what alien intelligence might look like or how it might manifest. That changed in the 20th century. Radio astronomy provided a tool for searching across interstellar distances. The realization that electromagnetic signals could propagate through space at light speed, carrying information across cosmic voids, opened the possibility of detecting artificial transmissions from civilizations around other stars. The first modern search for extraterrestrial intelligence began in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby Sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals at the hydrogen line frequency of 1,420 megahertz. He detected nothing, but the search had begun. Over the following decades, SETI searches expanded in scope and sophistication. More frequencies were monitored, more stars were targeted, more hours of observation time accumulated. The searches detected many signals of interest, brief spikes of radio energy that seemed artificial in origin. But none could be confirmed. None repeated. None proved to be messages from alien civilizations. The most famous was the WOW signal in 1977. For 72 seconds, the Big Ear telescope in Ohio recorded a narrow-band signal that matched expectations for an artificial transmission. The signal was strong, far above background noise. Its frequency was close to the hydrogen line, where astronomers expected intelligent species might broadcast. The computer printed out the data stream, and astronomer Jerry Emmons circled the relevant section and wrote, "Wow," in the margin. The WOW signal was never detected again. Despite decades of follow-up observations targeting the same region of sky, nothing similar ever appeared. Explanations involving passing comets or hydrogen clouds have been proposed but remain contentious. The signal remains unexplained, neither confirmed as artificial nor definitively attributed to natural sources. This pattern repeated in other cases. In 2007, astronomers using the Parkes telescope in Australia detected fast radio bursts, intense pulses of radio energy lasting milliseconds and arriving from distant galaxies. Initially mysterious, these bursts were eventually recognized as natural phenomena, probably involving magnetars or colliding neutron stars, not aliens. In 2015, the star KIC 846282, also known as Tabby's star, exhibited unusual dimming patterns that defied explanation through known stellar physics. Some researchers suggested the dimming might result from megastructures built by an advanced civilization to harvest stellar energy. Years of observation revealed the dimming was more likely caused by clouds of dust or debris orbiting the star, not aliens. In 2017, Oumuamua's anomalous acceleration sparked debate about light sails and artificial origin. Natural explanations involving outgassing hydrogen became the consensus view, not aliens. The pattern is clear. When astronomers encounter phenomena that do not fit immediately into understood categories, speculation about artificial origin arises. Media coverage amplifies the speculation. Public interest spikes. Then natural explanations emerge, the excitement fades, and the phenomenon joins the catalog of understood or partially understood astrophysical processes. Not aliens. Never aliens. This history creates a default assumption among scientists that any new anomaly will follow the same arc. Initial mystery, speculation, resolution through natural mechanisms. The assumption is statistically justified. The universe contains countless natural phenomena capable of producing unusual observations. The number of phenomena we have definitively attributed to artificial origin is 0. But statistical reasoning has limits. The fact that all previous searches have found natural explanations does not prove that all future searches will. The absence of confirmed alien contact does not prove that aliens do not exist. It proves only that if they exist, they have not contacted us in ways we have definitively recognized. And that qualifier matters. In ways we have definitively recognized. Perhaps aliens have contacted us, or at least passed through our neighborhood, and we dismissed the evidence as natural phenomena because we were not prepared to recognize artificial origin when it appeared. This possibility is what drives Dr. Loeb's insistence on taking 3I Atlas seriously as a potential technological artifact, not because the evidence is conclusive, not because artificial origin is the most probable explanation, but because the consequences of incorrectly dismissing real evidence are so profound that even low-probability hypotheses deserve rigorous investigation rather than reflexive rejection. The philosophical question underlying this debate is how to balance skepticism and openness. Skepticism protects against false positives, against seeing patterns that do not exist, against claiming discoveries that later embarrass the claimants. Openness protects against false negatives, against missing real discoveries because they do not fit expectations, against allowing assumptions to blind us to revolutionary observations. Science requires both skepticism and openness. Too much skepticism produces conservatism that rejects legitimate anomalies. Too much openness produces gullibility that accepts spurious claims. The ideal balance point lies somewhere in the middle, but exactly where depends on context, on stakes, on the specific claims being evaluated. For 3I Atlas, the stakes are extraordinary. If the object is natural and we investigate it as potentially artificial, we expend resources and attention that could have been directed elsewhere. But we gain valuable data about interstellar objects, and we refine our methods for distinguishing natural from artificial phenomena. The cost is limited. The benefit is real. If the object is artificial, and we dismiss it as natural, we miss the most significant discovery in human history. We fail to recognize evidence of extraterrestrial intelligence when it passes through our solar system. The cost is incalculable. The benefit of being cautious, of protecting scientific credibility, becomes meaningless when weighed against what is lost. This asymmetry in consequences argues for thorough investigation. Better to look closely and find nothing than to glance casually and miss everything. Better to risk being wrong about artificial origin than to risk being wrong about natural origin. The scientific community remains divided on whether this reasoning justifies the level of attention 3I Atlas is receiving. But the attention continues regardless. The observation campaign proceeds. The instruments are positioned. And tomorrow, October 29, Perihelion arrives and the testing begins. What exactly will those tests reveal? The energy conservation test proposed by Dr. Kaku is straightforward in principle but challenging in execution. Measuring an object's velocity with sufficient precision to detect small deviations from gravitational predictions requires accounting for many sources of error. Earth's atmosphere distorts the light from celestial objects, making precise position measurements difficult. Ground-based telescopes must correct for this distortion using adaptive optics or by taking many short exposures and selecting the sharpest ones. Space-based telescopes avoid atmospheric distortion but have their own challenges involving instrument calibration and thermal stability. The object's rotation complicates matters. As 3I Atlas tumbles through space, different surfaces face the Sun at different times. Outgassing varies across the surface, creating thrust that changes with rotation. Modeling this thrust requires knowing the rotation period, the shape of the nucleus, the distribution of volatile materials, and how each of these factors responds to changing solar distance. Dr. Seligman's team has been working to refine these models using observations gathered over the past 3 months. Their preliminary results suggest the rotation is complex, probably not a simple spin around a single axis, but a tumbling motion involving multiple axes. This makes predicting outgassing patterns more difficult. Despite these challenges, the measurements will be made. Multiple facilities will independently determine 3I Atlas's trajectory before and after perihelion. If the results agree and show energy conservation within measurement uncertainty, the natural hypothesis is supported. If the results show unexplained acceleration, further investigation is required. The spectroscopic observations seek different information. By analyzing the light from 3I Atlas, astronomers can identify which elements and molecules are present in the coma. Each substance absorbs and emits light at characteristic wavelengths, creating a unique fingerprint that reveals its presence. The nickel emission that Dr. Seligman's team detected appears as bright lines in the spectrum at specific wavelengths corresponding to nickel atoms excited by solar radiation. The presence of these lines without corresponding iron lines is the anomaly that sparked initial interest. Continued monitoring will track whether this pattern persists, whether iron eventually appears as the object warms further, whether other unexpected elements emerge. If the chemical composition remains anomalous, if the ratios of elements and molecules continue to differ significantly from solar system comets, then 3I Atlas's formation environment must have been very different from our own. This alone would be scientifically valuable, constraining models of planet and comet formation around other stars. But if the composition shows features impossible to explain through any known natural process, if substances appear that require industrial synthesis, or if isotope ratios suggest artificial enrichment, then the case for technological origin strengthens dramatically. The radio searches face the challenge of distinguishing artificial signals from natural noise and terrestrial interference. Earth's atmosphere and ionosphere emit radio energy at various frequencies. Human technology produces radio signals at many frequencies, from broadcast stations to satellites to radar systems. Even with radio quiet zones and careful filtering, separating a faint potential signal from 3I Atlas from this background requires sophisticated analysis. The search focuses on narrow-band signals, transmissions concentrated at very specific frequencies. Natural processes produce broadband emissions, energy spread across wide frequency ranges. Artificial transmissions often use narrow-band signals because they are more efficient for communications and easier to detect against background noise. If 3I Atlas contains active electronics, if it is transmitting data back towards some distant origin or communicating with other objects in the solar system, those transmissions might be detectable. The power required would depend on the distance to the intended receiver. Transmitting to another star system would require enormous power. Transmitting to smaller probes nearby would require much less. The geometry also matters. If 3I Atlas is transmitting but the beam is directional, aimed at a specific target, Earth might not intercept the beam. We would detect nothing even if transmissions are occurring. This is one of many ways that absence of evidence does not constitute evidence of absence. The surface imaging seeks geometric patterns that might indicate artificial structures. Natural objects shaped by gravity and impacts have irregular surfaces with features distributed randomly. Artificial objects might show straight edges, regular spacing of features, symmetry indicating design rather than natural formation. At the distances involved, even Hubble and Webb cannot resolve fine details on 3I Atlas's nucleus. The object will appear as perhaps a few pixels across, with the coma making even that uncertain. Detecting obvious geometric patterns would require those patterns to be large-scale, visible even at low resolution. If 3I Atlas were a spacecraft, what might it look like? Science fiction offers many visions: sleek metallic hulls, glowing engines, obvious technological forms. But real spacecraft designed for interstellar travel would prioritize different features. Radiation shielding would be essential, probably involving thick layers of material. Thermal management would be critical, requiring systems to dissipate heat generated by onboard systems while preventing freezing of essential components. An interstellar probe might look less like a spacecraft and more like a comet intentionally camouflage designed to avoid detection, or simply the practical solution of surrounding delicate instruments with protective ice. If 3I Atlas were artificial, its comet-like appearance might be deliberate design rather than proof of natural origin. This possibility cannot be tested directly. We cannot board 3I Atlas, cannot drill through the ice, cannot examine what lies beneath the surface. We can only observe from distance and infer from those observations what the object might be. The spacecraft particle collection offers the most direct sampling opportunity. If Europa Clipper or Hera pass through 3I Atlas's tail, if they collect dust particles, those particles can be analyzed for composition and structure. Natural particles formed through accretion and ice condensation have characteristic morphologies. Artificial particles might show processed structures, refined materials, isotope ratios inconsistent with natural formation. The analysis would be limited by instrument capabilities. Neither spacecraft was designed for this purpose. Their particle detectors are optimized for different targets: Jupiter's moons in Europa Clipper's case, asteroid material for Hera. But they can still provide data, can still identify gross anomalies even if fine details escape detection. The timing is fortunate. When 3I Atlas was discovered in July, Europa Clipper had already launched on its journey to Jupiter. Hera was preparing for launch to study the aftermath of the DART mission's impact on the asteroid Didymos. Neither mission was designed with 3I Atlas in mind. Yet their trajectories will carry them through the tail region at opportune times, positioned by the geometry of orbits determined months before the comet's discovery. Coincidence? Or something more? The thought has occurred to multiple researchers that 3I Atlas's trajectory seems remarkably convenient for observation by spacecraft that happen to be launched in 2024 and early 2025. The probability of this alignment is difficult to calculate, but certainly low. Does it mean anything? Probably not. Probably just another coincidence in a story filled with improbable events that, taken together, create a pattern that seems meaningful but reflects only the human tendency to see patterns everywhere, even in random noise. Or perhaps it means something. Perhaps the trajectory was not random. Perhaps 3I Atlas's arrival was timed to coincide with a period when humanity had spacecraft positioned to intercept it. Perhaps our development of space capability triggered interest from watchers who then sent a probe to investigate. This is speculation piled on speculation, hypothesis without evidence, imagination running ahead of data. But it is the kind of speculation that 3I Atlas provokes, the questions that arise when anomalies accumulate and conventional explanations strain. The coming weeks will provide answers or at least narrow the range of possibilities. Perihelion tomorrow, Continuous observations through November. Closest Earth approach in December. Spacecraft encounters. Accumulated data from hundreds of observers feeding into analysis pipelines that will produce papers, conferences, debates that extend into 2026 and beyond. But the critical moment is tomorrow. The test that Dr. Kaku proposed, the measurement of energy conservation, happens at perihelion when the object is moving fastest and any propulsive thrust would have maximum effect. If 3I Atlas is artificial, if it intends to maneuver, tomorrow is when it will act. And if it acts, if excess energy appears, if the trajectory changes in ways that cannot be attributed to outgassing or gravitational perturbations, then everything changes. The debate shifts from whether we should investigate artificial origin to what the artificial origin means. The question becomes not, is it aliens, but what do the aliens want? This question has troubled thinkers for decades. If extraterrestrial intelligence exists, if it has developed interstellar travel, what would its motives be? Why would it visit our solar system? What would it want from or with humanity? Science fiction explores many possibilities. Benevolent first contact, sharing of knowledge and technology, malevolent invasion, resource extraction or conquest, indifference, species so advanced that humanity barely registers as worthy of notice, observation, scientific curiosity directed at emerging civilizations. Dr. Loeb's July 2025 paper outlined the binary, intentions either benign or malign, but reality offers more nuance. Intentions might be mixed. Benevolence from one perspective might appear as interference from another. Scientific observation might violate privacy without intending harm. Contact might be desired by the visitors, but disastrous for the contacted. The history of contact between human civilizations offers cautionary examples. When technologically advanced societies encountered less developed ones, the results were often catastrophic for the less developed. Not always through deliberate malice, often through disease, through disruption of social structures, through economic exploitation that occurred even when individual actors meant no harm. Would extraterrestrial contact follow similar patterns? Would humanity be the less developed civilization facing disruption? Or has our development of space technology and nuclear weapons moved us into a category that merits different treatment, recognized as potentially dangerous, even if currently limited to a single planet? These questions cannot be answered through speculation. They require data. They require contact, or at least unambiguous evidence of extraterrestrial technology. And 3I Atlas might, possibly perhaps, provide that evidence, or not. Probably not. Most likely the object is a comet, unusual in its specifics but natural in its origin, shaped by processes that operated in another stellar system billions of years ago, and left imprints we can study to refine our understanding of how planetary systems form and evolve. Either outcome advances knowledge. Either outcome represents successful science. But one outcome changes everything, while the other changes only details. We stand at the threshold, hours from perihelion, hours from tests that will reveal whether energy is conserved, whether chemistry is explicable, whether the anomalies resolve or deepen. Hours from data that will either confirm assumptions or shatter them. The world watches, not just scientists, but the broader public, aware that something unprecedented might be occurring, uncertain what it means, but sensing that significance. Social media discussions range from rigorous analysis to wild speculation. News coverage on every continent reports the approaching perihelion. Even people with no background in astronomy know the name 3-Eye Atlas, know that tomorrow might bring revelations. This level of public engagement with astronomical observation is rare. Eclipses draw crowds. Major spacecraft missions attract attention. But routine observation campaigns, the patient accumulation of data that forms the foundation of astronomical research, usually occurs without public notice. 3-Eye Atlas has broken that pattern. The combination of interstellar origin, unusual features, and prominent scientists willing to speculate publicly about artificial origin has captured imagination in ways that normal cometary observation never could. Whether this is healthy for science, whether public expectations can be managed if the object proves mundane, remains to be seen. But for now, the attention focuses resources and effort on maximizing what can be learned. The observation campaign is better funded and better coordinated because of public interest. Facilities that might have allocated minimal time to 3-Eye Atlas have instead prioritized it. Citizen scientists who might have observed other targets have focused on this one. If 3-Eye Atlas teaches humanity nothing else, it demonstrates that the search for extraterrestrial intelligence can inspire. It can motivate. It can bring together diverse communities in common cause. And regardless of what Perihelion reveals, that inspiration has value. The clock advances. October 28 becomes October 29. Somewhere above, moving at tens of kilometers per second, 3-Eye Atlas plunges toward its closest approach to the sun that gives life to Earth, that illuminates the solar system, that has shone for 5 billion years and will shine for 5 billion more. The sun does not care about 3-Eye Atlas, does not care whether the object is natural or artificial, whether humanity discovers profound truths or confirms existing knowledge. The sun burns hydrogen, fuses it into helium, releases energy that flows outward through radiation and convection until it reaches the photosphere and escapes as light and heat. That light travels 8 minutes to Earth. It travels 70 minutes to 3-Eye Atlas at Perihelion. And when it arrives, when photons emitted by nuclear fusion strike ice formed around another star, something will happen. Material will sublimate, energy will transfer, motion will change, and we will watch. We will measure, we will analyze, and we will learn something about the universe we inhabit, about whether intelligence has transcended the bounds of single planets, about whether we are alone or part of a larger community that spans the cosmic distances between stars. Tomorrow, the answers begin. Tonight, we wait, and in the waiting, in the anticipation of discovery, we are all explorers together, standing at the edge of knowledge, ready to step forward into whatever tomorrow reveals. 3-Eye Atlas approaches. The moment arrives, and with it comes possibility. Extraordinary or ordinary, revolutionary or routine, but real. Data waiting to be collected, questions waiting to be answered, a universe waiting to be understood a little better than we understood it before. This is why we explore, not for certainty, but for discovery, not to confirm what we believe, but to learn what we do not know. And sometimes, rarely, what we learn changes everything. Tomorrow we find out which kind of day this is. Thank you for being with us. Please subscribe and leave a like.